Okay, Chapter 11, Section 10, Taylor and Maclaurin series. So let's begin this section by quickly looking over some of the stuff we've already learned in the prior two sections. So if we look in our book real quick, um, here's our textbook. We learned power series in Chapter 11, Section 8, right? So this was an introduction, our first introduction into a power series. The more general form of a power series was given here. A more general form, a power series centered at A. So it's a power series centered at A, or power series in x minus A, or a power series about A. Okay, so we learned all about power series in Chapter 11, Section 8. And then moving on, then we went over to Chapter 9. And in Chapter 9, we ran into this guy in Chapter 9. So given a power series, so if the power series is something that fits this form, has a radius of convergence r greater than 0, then that means that the function f of x, which is described as a power series, can be expanded this way, right? Which this is the Riemann sum expression of this. And then what we learned in that section was that we can then take derivatives or we can integrate, right? So we can take the derivative of f of x, or we can take the integral of f of x, and then we learned that it was okay to do it term by term by term by term, right? That's true only for a power series, right? So this business of doing it one at a time out to infinity, right? Infinity can be a tricky thing. So it shouldn't just be taken for granted that you can always just do things and continue that pattern for infinity. Sometimes you're going to find that that's not really true. But for this case, we're working with power series. Within the confines of power series, it is true we can take the derivatives term by term by term and establish a pattern. So we did that, and that's what we worked with in the previous section. Okay, so how is all of this going to be connected? We're going to go back to working with this, a power series function, and we're going to go ahead and take the derivatives in the following way. So suppose f of x has a power series representation at a, right, or about x minus a, then that means that f of x can be expressed as a power series, and from 0 to infinity of some c sub n x minus a to the power of n. And this is for x minus a absolute values to be less than capital R. Okay, so let's expand this guy out. Right, so the first one is going to be c sub naught, right? We replace all those n's there with a, well, actually, okay, so the first one, that value there is a 0 raised to the power of 0. That's when n equals to 0. That's a 0, that's a 0. And then the next one is going to be a 1, so that's going to be c sub 1 raised to the power of 1. And then c sub 2 raised to the power of 2. And then c sub 3 raised to the power of 3, c sub 4 raised to the power of 4, c sub 5 raised to the power of 5, and so on and so forth, right, forever. But somewhere along the line here, I'm going to say that there is some nth value over here, right? As we progress forward, there will be some nth value That'll be c sub n raised to the power of n. And it doesn't stop there, of course, it keeps going. So the one right next to that one is going to be the term that is c sub n plus 1 to the power of n plus 1. And the one after that is going to be plus c sub n plus 2 to the power of n plus 2. And then it goes on, right? Plus dot, 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 dot. Plus dot, 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 forever, right? So I'm just pointing out that somewhere along the path, there's the nth one, and then the n plus 1, and then plus 2, and it just keeps going on forever, right? Okay, so this is a nice expanded one. Okay, well, we can simplify these just a little bit. First of all, to the power of 0, we've taken the liberty of calling that a 1. So if we just simplify that to call that a 1, then this expression can be rewritten as c sub naught, power x minus 1 to the power of 0, that's just going to be a 1, plus c1 x minus a, plus c sub 2 x minus a squared, plus c sub 3 x minus a to the third power, plus c sub 4 x minus a to the fourth power, plus c sub 5 x minus a to the fifth power, plus dot, 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 and then there's these guys, c sub n x minus a to the nth power, plus c sub n plus 1 x minus a to the n plus 1 power, plus c plus 2 x minus a to the n plus 2 power, plus dot, 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 dot. Going on forever, right? So I'm just pointing out that somewhere along the way there's the nth one, and the one next to it is the n plus 1, then n plus 2, then n plus 3, and then it keeps going on toward infinity. Okay, so what we're going to do is, well, first of all, we've already noticed in the previous section that we can figure out what this constant is, right? Because we noticed that if all of these terms, except for the first one, all of these terms have a factor of x minus a. So if we replace that x with a in this case, that means that this part of it would be 0, and then this part of it would be 0, and this part would be 0. So all of those terms going on forever would all cancel out, and then the only thing that survives is this naught, c sub naught. So we can figure out the value of that one, right? So, for example, what I'm saying is this. So if I just copied all of that and I left all the x's blank, so now we're going to say let's let x equal to a, and so we replace all those x values with an a. A goes there, 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 dot, 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 all the way out to the nth term. A goes there, the one right next to it, the a, the power of n plus 1, and then to the power of n plus 2, and so on for infinity. Well, every one of those terms from starting here all the way out to infinity, all of these are going to become 0. 0, 0, 0, 0, 0, 0, 0, 0, forever. And so what we have left over is just this part right here. So that means that c of a equals to c naught. Okay, so going back to this statement here, well, what we just did is we figured out the value of this one, right? Instead of just saying it's c naught, just some arbitrary c naught, we can say, well, that c naught is actually f of a. I can stick that right in there, so I'm going to do that right now. Okay, so I replaced that C naught with an f of a. Okay, we did something like that already, so maybe it's not, hopefully not that new. But what we want to do, our goal now, is going to be to figure out the next few of these. Figure out C sub 1, C sub 2, C sub 3, and then maybe figure out a pattern for all of them. That's what we're going to do. Now, how are we going to accomplish that? We're going to note that, as we just reviewed, we are allowed to take derivatives. So if we take the derivative of this function, whether this one or this one, right, this is just going to be some constant. After you plug in an a into your function, this will give you some constant. So constant with respect to x. Now there's no x's in there, so it can be treated as a constant. So we can just take the derivative. So let's go back to this guy here, and we're going to take its derivative with respect to x. So we're going to take f prime of x and say that that's equal to, and then here's the original function, so going out to there, we want to take the derivative with respect to x of this entire thing. That's what we want to do. And so we're going to go term by term. All right, so then that first derivative, f prime of x, is equal to, well, this is a constant, right, with respect to x. So this is just going to be a 0 plus, and now this has power 1, so we bring down the 1 in front, and we'll have c1 times 1, and then this then becomes 1 minus 1, which is going to be to the power of 0. So then this term disappears. Good. This will become x minus a. I'll put it here. This will become x minus a to the power of 1 minus 1, right? Because this has a 1 here. So if I subtract 1 from the exponent, it becomes 0. And then anything with the 0 power becomes 1. So this whole term becomes 1. And just for the sake of simplifying this really already messy thing, let's just leave it as a 1. Right? So there's just a 1 there. Plus, okay, the next term, we have a c sub 2 times, and then we bring down that 2, and then we end up with a power of 1, so that'll become x minus a to the power of 1, plus, and then c sub 3, we bring down that 3, becomes times 3, times x minus a to the power of 2, plus c sub 4, and then to the power times 4, times x minus a to the power of 3, plus c sub 5 times 5, x minus a to the power of 4, plus dot, 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 dot. And let's see what happens to these guys. We end up with plus, and then this becomes c sub n times x minus a to the power of n minus 1, right? So we bring down that n now down as a factor, and then we subtract 1 from the exponent, plus, and then the one right next to it is going to be c sub n plus 1 times n plus 1 times a minus a to the power of, well, we subtract 1, we just get a power of n. Right? And then there's the next one, but that's okay. Let's leave it alone and say keep going that way. Okay, so now what we have here is a new function, the first derivative of the function. And what we want to note is that, once again, almost all the terms are going to have a factor of x minus a, starting here. X minus a, x minus a, x minus a. So if we replace all those x values with an a again, just like we did up there, we're going to get a situation where almost all the terms become 0. Okay, so all I did was copy this exact same first derivative, and then I got rid of all the x's all the way along. And now what we're going to do is we're going to replace x equals to a into this. So it's the first derivative of the function evaluated at a, so that becomes an a. And then we have an a there, and 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 we have an a there. Okay, and so you can see, this goes on forever, every single term is going to have a 0. a minus a is 0, so this whole thing becomes 0. A minus a is 0, so this whole term becomes 0. A minus a is 0, that whole term becomes 0. 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 And the only thing that survives all of this is this. So we end up with the statement that the first derivative of the function evaluated at a is equal to c sub 1 times 1. So once again, if we just simplify that a little bit, 1 times anything is still 1. But just for the sake of the pattern, I'm going to move this over here and say that it's equal to f prime of a over 1 equals to c sub 1. Equals to c sub 1. Okay, we'll see why I did that in a second. But what we've accomplished then is that now we know the value of c sub 1. We found out the value of c sub 0, and now we have the value of c sub 1, c sub 1, c sub 0. So going back up here again to the original power distribution, this one, now I know the value of c sub 1. C sub 1 is actually equal to f prime of a. So let me squeeze that into here. Okay, so the c sub 1 is f prime, the first derivative of the function evaluated at a, divided by 1, times the factor of x minus a. That's what we have so far. Okay, let's keep going. Let's do a couple more, and then we see if there's a pattern that we can establish. So, you guessed it, to find the next one, what we're going to do is continue on this pattern of finding derivatives and then evaluating the function at x equals to a to see our result. Okay, so now if we go back to this one right here and want to take the next derivative, then the next derivative is going to be this. So the second derivative is equal to going to the first derivative and taking the derivative of that, right? So the derivative of the first derivative is going to give us the second derivative. Okay, so then we got to go term by term and take derivatives. So the derivative of 0 is 0. That's just going to disappear, 0. And then here we have a constant with respect to x, so this is also going to be 0. All right, so here is the pattern we begin to get. The second derivative with respect to x is going to then be equal to 0, and then there's another 0 from here and there. And then we'll get this term. Now the pattern, I'm going to move these around since I don't like that I started putting the c sub 2 on the inside. So I'm just going to flip these around, bring this out in front, and we end up with the 2 times a 1 times a c sub 2. And then there's this x minus a to the power of 0, right? When we take a derivative, we reduce the exponent by 1. So just like before, this is really a 1. So let's just get rid of it. Otherwise, it's going to get super duper messy. So there's just a 1 there. And let's keep going with our pattern. The next one is going to end up being this 3 was already there. 3, and then there's a 2 from the exponent. And then there's a c sub 3, and then there'll be an x minus a to the power of 1 plus a c sub 4. Oops. And then a 4 times 3 times c sub 4 x minus a to the power of 2 plus 5 times 4 times c sub 5 x minus a to the power of 3 plus dot 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 dot. Okay, and when we get to the nth one, we'll have n, and then that exponent is n minus 1. We'll bring that in front. Then there will be a c sub n. Then there will be a c sub n times x minus a to the power of n minus 2, right? We subtract 1 from the exponent. Let's go to the one right next to it, plus, and then this pattern is then going to be n plus 1. That was already there. Bring down that exponent. That'll be an extra n. times n, and then a c sub n plus 1, and then an x minus a to the power of n minus 1 term, and then this continues, right? Plus dot, 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 forever. Okay, so here's our second derivative. I'm going to simplify this just a little bit by getting rid of those initial zeros, making some space here. So this is equal to okay, so here is our second derivative. And again, just like before, notice that almost all the terms have an x minus a, almost all of them except for that first one over there. So we're going to do the same thing we've been doing from before. We're going to figure out what happens when we let x equal to a, x equal to a. Okay, so all I did is copy this second derivative from this polynomial and copied it down here. And I removed all those x values. And so now we're going to replace the x with an a. A goes there. We have an a minus there, an a minus a there, an a minus a there, a minus a there, and an a minus a there. And just like before, all of these terms have a 0, so they become 0. A minus a is 0, 0. This becomes 0, 0. This becomes 0, 0. This becomes 0, 0. And so the only thing that survives is this. So let's recopy that now. So we're saying that the second derivative, with respect to a, is equal to 2 times 1 times c sub 2. And just like before, we want to solve for c sub 2, so we're going to divide both sides by this 2 times 1. And so we'll end up with the second derivative with respect to a divided by 2 times 1 is equal to c sub 2. So we have an equation for c sub 2. Once again, if we go back up to the top, we go back up to our original expanded power series, we have a value for this guy now. So we're going to replace this with what I just found. So this guy then becomes, let's sneak it in there, okay, so all I did is I snuck in this value of c sub 2, which we just discovered. It's the original function. We take the second derivative of our function, evaluated at a, divided by 2 times 1, and then that becomes the c sub 2, and then we just kept this term of x minus a. So what we're doing is we're slowly figuring out all these values of c from the original expansion of our power series. Right? We're figuring out the coefficients to go in front of each of the terms that have an x minus a. Right? So let's do 1 or 2 more of these, and then we'll do it in general and see a pattern that can be established. Okay, so let's do the next one. So just like before, we want to take a new derivative to find the next one. We already took the first derivative, we took the second derivative, we want to take the third derivative. But right around the third derivative, maybe the fourth derivative, we switch notation a little bit because doing these little tick mark things is going to start to get annoying. The fifth derivative, I'm really going to do 1, 2, 3, 4, 5 little tick marks, seventh derivative, eighth derivative. It becomes a little cumbersome to have to do it this way. So we adopt a new notation style to deal with these. Okay, and so the notation style is going to be that instead of putting a little tick mark thing, we're going to replace it with a little number that indicates how many derivatives we've been taking. So instead of doing the second derivative this way, 2 little tick marks, we're going to rewrite it as parentheses 2 like this. And just so people don't confuse it as this function being squared, that's why we wrap it around parentheses. And that's just notation style. The second derivative of the function evaluated at a. And then we're going to do the same thing here. So I can kind of backtrack and replace all of these guys with this new notation style, this different notation style, and say that's the second derivative, that's the second derivative. And then coming back up here, I'm going to do the same with these guys. So notation style, we're going to say, well, okay, this guy is the second derivative, the second derivative of the function. And now, well, if that one was the second derivative, that means that this one little tick mark like this, these were all first derivatives. So we do it this way, a little parentheses, a 1, a little parentheses with a 1, a little parentheses with a 1, a little parentheses with a 1. And then we do that over here as well. And then a little parentheses with a 1, right? So this is the first derivative of my function. Okay, so if this is the first derivative of the function, then the original function can be thought of as the no derivative, right? The zero derivative. So we also put a little 0 there if we wanted to, and that's just to be consistent with our results. Okay, so the first derivative means that we didn't take a derivative at all. I'm sorry, the 0th derivative means we didn't take a derivative at all. It's the original function. Okay, so going back up to this guy then, we can also rewrite it. Instead of the little tick marks, we can put a to the power of 0 there, to the power of 1 there, the second derivative there. So let's fix that as well. To the power of 0, so the 0th derivative of the function evaluated at a, and then this guy is the first derivative of the function evaluated at a. And then this one turned out to be the second derivative of our function evaluated at a. Okay, so now we're down to our third derivative, and we have new notation for it, but it's basically this guy. So we're going to take the derivative. So here is our second derivative right here. So we're going to take the derivative of this, so that'll be our third derivative. So f of the third derivative of x is going to be equal to the derivative with respect to x of this guy, right? The second derivative, we take another derivative, we'll get to the third derivative. Good. So then again, we go term by term by term, and so we get that the third derivative with respect to x is going to be equal to, well, this is just going to be some constant again. So this whole term here then becomes 0, right? Some constant with respect to x because there are no x's in there. And then just like before, we start to notice this pattern that this will be 3 times 2, and then we bring that 1 out in front. So we'll end up with 3 times 2 times 1, and then c sub 3. And then just like before, this term becomes x minus a to the power of 0, which is just going to become 1. So we don't have that term anymore. So let's just get rid of it. And then the next one here is going to be a 4 times a 3 times the 2 that you bring it in front, and then subtract 1 from there. So we end up with 4 times 3 times 2 times c sub 4 x minus a to the power of 1 plus, and now 5 times 4 times 3 times c sub 5 x minus a to the power of 2 plus dot, 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 and then out of the nth term, we had an n minus 1. Now we bring that in front, and we end up with another term of n minus 2, c sub n, and then x minus a to the power of n minus 3. Okay, so let's take one more, run the one right next to it, plus this will be n plus 1 times n times, and now we bring that exponent out in front, so we'll end up with an n minus 1, and then c sub n plus 1, and then we have a term of x minus a to the power of n minus 2. Plus dot, 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 so on and so forth, forever. Okay, but I think the pattern is starting to pop out. Okay, so now we have the third derivative. Oops, don't forget to put this guy here around with parentheses. Okay, so it's the third derivative of the function equals to this. And now, just like before, we want to evaluate all of this at x equals to a, because we notice again that almost all the terms will have this term of x minus a, almost all of them except for that first one. Okay, so so this becomes x equals to a. We want to evaluate this third derivative when x equals to a. So I just copied this whole thing here, the third derivative of our function, and erased all the x terms. And now I'm going to replace the x with an a. So there'll be an a there, 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 and there will be an a there. Right? So all of the terms, almost all of them out to infinity, have a term of a minus a except for that first one. So that means that this will be 0, and that'll be 0, and then that'll be 0, and then that'll be 0, right? Going out to infinity, all of them become 0. So the only thing that survives is this one. So we get that the third derivative evaluated at a is equal to 3 times 2 times 1 times c sub 3. And just like before, I'm going to solve for c sub 3 by dividing both sides by 3 times 2 times 1. So we get that the third derivative evaluated at a divided by 3 times 2 times 1 equals to c sub 3. Good. So now what we have an equation for c sub 3, and also I think now the pattern is really, really clear. So now we can go back again to our original expansion, which is way up here. Here it is, right? So here is that original power expansion. And so now we have a value for this guy. So now we can replace this and rewrite the whole thing. So now this term in our original power series in general, a power series expansion in general, I'm just going to squeeze it right in here. So it's going to be f of 3 evaluated at a divided by 3 times 2 times 1. And then there'll be this term of x minus a to the power of 3. Good, so that's just that term. So there's an addition there, and then there's an addition there. So what have we accomplished? We have our original power series, that's this guy right here, going on forever. And we were able to figure out the value of c sub 0. That was this one, the 0th derivative, or the original function evaluated of a. And then we found c sub 1, which is equal to the first derivative of the function evaluated at a divided by 1. And then we found the value of c sub 2, which is the second derivative of the function evaluated at a divided by 2 times 1. And now we just found that c sub 3 is equal to the third derivative of our function evaluated at a all over 3 times 2 times 1. So based on that, I think it's pretty easy to see what the next few of these are going to be. We've established the pattern, right? So let's just guess what the next one's going to be. Just based on this pattern I've established, I can guess what this c sub 4 is going to be. Okay, so just based on the pattern we've seen before, look, c sub 2 was really the second derivative. So this one is going to end up being the fourth derivative. So we take our original function, raise it to the fourth derivative, and then evaluate it at a, divided by, and then there's this countdown of 4 times 3 times 2 times 1 times 1, and then there'll be the term x minus a to the power of 4. Right? So that's the pattern we've established. And so based on that, we're ready to see what happens in general, right? As we jump out to the nth value, we can figure out what this is going to be. Right? So as we start taking more and more derivatives, we see that every time we take a derivative, we bring down the exponent. So this little countdown begins to happen. 4, 3, 2, 1. The next one's 5, 4, 3, 2, 1. So we can guess what's going to happen when we go out to the nth derivative. Okay, so now dot, 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 dot. We've taken a bunch of derivatives. When we get down to the nth derivative, evaluated at x, well, all of these terms are going to become 0 somewhere along the way, right, as we keep going and taking derivatives. The fourth derivative, this will be a constant, so that becomes 0. And then we bring this out in front, and so we'll have that little countdown of 4, 3, 2, 1. And then the derivative after that, well, that will become a constant, and so then we'll have this little countdown of 5, 4, 3, 2, 1, and so on and so forth. So as we go all the way down to the nth derivative, the first one that has a constant is going to end up being this n times n minus 1 times n minus 2 dot, 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 all the way until we get like a 3 times a 2 times a 1, something like that, times c sub n, and then there will be a x minus a to the power of 0 term, which we've been doing this whole time, and we see that that term is 1, so we just don't even bother writing it. Okay, that's just going to be a 1. And if we pay attention to the one right next to it, the one right next to it is going to have this pattern of n plus 1. And now if we pay attention to the one that came after it, just to make sure that the pattern is continuing, that's starting here. See, the countdown started at n plus 1, so the one right next to it would be n plus 1 times n minus 1 times n minus 2 dot, 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 until we get to this countdown of like 3 times 2 times c sub n plus 1 x minus a to the power of n to the power of 1. That's the pattern we're going to see. And the one that comes after that, just to kind of make sure the pattern continues, this one's going to start with a countdown of n plus 2, and then n plus 1, and then n minus 1, and so on and so forth. And it's going to end up at 3. It's going to end up at 4 times 3, and then it's going to stop there. And there will be a c sub n plus 2, and then an x minus a to the power of 2 term, and then it'll continue forever, right? Dot, 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 forever. And just like we've been seeing before, this means that almost all the terms from infinity on down will have a factor of x minus a, except for that very first term. So when we evaluate this function at x equals to a, right, we come in here and go, let's let x equal to a. That means that we're going to replace this guy with an a, we're going to replace this guy with an a, and so on and so forth forever, going that way. And that means that all of these terms, that includes this whole thing here, this whole term is going to become 0, this whole term is going to become 0, and so on and so forth. So the only thing that survives when we take the nth derivative and evaluate our function at a is going to be this. So let me write that down. We're going to end up with f of the nth derivative of f evaluated at a is going to be equal to n times n minus 1 times n minus 2 dot 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 all the way down to 3, 2, 1, something like that, 3, 2, 1 times c sub n. And now to solve for c sub n, we divide both sides of the equal sign by this. And so we get that the nth derivative, of our function evaluated at a divided by n times n minus 1 times n times n minus times n minus 1 times n minus 2 dot 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 all the way down to 3, 2, 1 equals to c sub n. And while this countdown here, a better way to do it, right? So 3 times 2 times 1, a better way to write that is 3 factorial. So a better way to write this would be n factorial. So this is f of n evaluated a divided by n factorial equals to c sub n. Good? Okay, so let's put it all together. Power series. So let's put it all together then. Suppose f of x can be represented as a power series centered at x equals to a with radius of conversion with radius of convergence r strictly greater than 0, then f of x can be expressed as this infinite sum of c sub n x minus a to the power of n, and this is for x minus a being strictly less than r. Okay, we already knew that. We can expand this guy. F of x then is equal to c sub naught plus c sub 1 x minus a to the nth power, to the first power, plus c sub 2 x minus a to the second power, plus c sub 3 x minus a to the third power, plus dot 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 dot. Somewhere down the road we have the nth one, so this is equal to c sub n x minus a to the nth one, and then this keeps going on forever, right? Okay, so what we just discovered is that the nth coefficient, the c sub nth coefficient, has a formula of its own. So now we know that c sub n is actually equal to the nth derivative of our function evaluated at a divided by n factorial. So that means that if we go back to here, we can replace all of these guys in the following way. So f of x is actually equal to f of a plus, and then f of the first derivative evaluated at a divided by 1 x minus a to the 1 power plus f, the second derivative of our function, evaluated a, divided by 2 times x minus a squared plus the third derivative of our function, evaluated a, divided by 3 times 2 times 1, which, okay, well, we can just rewrite that as 3 factorial times x minus a to the power of 3, right? So what we're doing is we're replacing all these coefficients, c sub n's, with these terms, plus, and then we keep going, and then the nth one out there is going to be the nth derivative of our function, evaluated at a, divided by n factorial times x minus a to the power of n plus dot, 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 dot. Right? So that's what we've just established. Okay, so let's look at the formal presentation of what this means from our book. So if we scroll on over to 10, okay, this is what we just discovered. If f has a power series representation, expansion at a, that is to say we have a power series that fits this general form of a power series, right, with a radius of convergence r, so here's our interval of convergence, then its coefficients are given by this formula, right? So we very painfully derived this formula right here. So this guy tells you how to find each one of these as a c sub n values. So we can replace c sub n by this guy. That's what happened here. So this, number 6, is an exact copy. They just copied this and then replaced the c sub n with this newfound formula. The c sub n is the nth derivative of our function evaluated at a divided by n factorial times, and then we keep this part of it, x minus a to the power of n. Okay, so if we expand that out, that must mean, just the way I wrote a second ago, that this is true. The original function that can be expressed as a power series, this one, can be written this way. So the first term is f of a plus f prime of a, so the first derivative of the function evaluated at a divided by 1 or 1 factorial, x minus a to the power of 1, plus the second derivative of our function evaluated at a divided by 2 factorial times x minus a squared plus the third derivative evaluated at a over 3 factorial x minus a to the third power, and so on and so forth. That's exactly what I just wrote. Okay, so this is called a Taylor series of the function at a, or about a, or centered at a, right? So this number 6 here is called a Taylor series. A special subset of the Taylor series expansion is something called a Maclaurin series. A Maclaurin series is just a Taylor series where it just so happens that the a happens to be a 0. So if we just replace the a's all along here with a 0, then we end up with this guy, right? X minus 0 is this, raised to the power of n. And then the nth derivative of a, the nth derivative of 0 gives you this. And so we have this, this expression, and this is what we call a Maclaurin series. So all Maclaurin series are Taylor series. They're a subset of Taylor series. But it's not true that all Taylor series are Maclaurin series, right? They're a proper subset. So let me write that over here. Okay, so this is a Taylor series, whether you have it in a condensed form using that Riemann sum, or if you expand it all out and use those little dots, dot, 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 dots, to show that that goes on for infinity, we have a Taylor series. Now, on the other hand, if you just happen to let a equal to 0, then each one of these things becomes 0. So we end up with so you just let a equal to 0, we'll have f of 0 there, the first derivative evaluated at 0, the second derivative evaluated at 0, the third derivative evaluated at 0, x minus 0, the nth derivative evaluated at 0, x minus 0, right? So we end up with this. And so that can be simplified a little bit, and we'd say that f of x then just becomes f of 0 plus the first derivative evaluated at 0 times x plus, and then the second derivative evaluated at 0 times x squared over 2. Or to establish that pattern, it's 2 times 1, or just 2 factorial. And then just to continue that pattern, we can also put 1 there, or 1 factorial. Either way, that's 1. Either way, that's just 2. Plus, and then we have the third derivative, the third derivative evaluated at 0 divided by 3 factorial times x to the third power plus dot, 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 dot. And then we end up with the nth derivative evaluated at 0 divided by n factorial times x to the nth power plus dot, 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 dot. Okay, so in the special case where we take a Taylor series and we let x equal to 0, we'll end up with something that looks like this, and then that can be expressed using the Riemann sum as this is equal to the Riemann sum as n goes from 0 to infinity of f, the nth derivative evaluated at 0 over n factorial times x to the nth power, right? So again, all I did is replace the a with a 0 there, and then a with a 0 there, and we have something called Maclaurin series, right? And this is for absolute value of x being strictly less than r. Good. So this one's called okay, so this is called the Maclaurin series. The more general form is called the Taylor series. The Maclaurin series are a proper subset of the Taylor series. So every Maclaurin series is a Taylor series that happens to have a equal to 0. But it's not true that every Taylor series is a Maclaurin series. Kind of like, do a terrible map here. Let's pretend. Wow, that's really ugly. But let's pretend that this is the USA, or at least the continental USA. USA. And then over here we have California somewhere doing this kind of a thing, right? So this one is California. California is a proper subset of the US, so every Californian is an American, but it's not true that every American is a Californian, right? Okay, so that's the same relationship we want to establish. The Taylor series is sort of the US here, and Maclaurins are a proper subset of it. Every single Maclaurin is a Taylor series, but it's not true that every Taylor series is a Maclaurin. Right? It's a proper subset. Okay, so what does all this mean? What are we going to do with all this? Okay, so let's look at an example. Okay, so find the Maclaurin series of the function f of x equals to e to the x. All right, well, right away we know that if f of x has an expansion, it's going to look like this. F of x equals to the sum as n goes from 0 to infinity. We know we're going to have to take the nth derivative evaluated at 0 divided by n factorial times x to the nth power, right? That's the general equation for a Maclaurin series. Okay, so we need derivatives. Let's start thinking about derivatives of the function. So we have the original function, f of x equals to e to the x. And then we're going to take the first derivative, and that's going to be equal to e to the x. And then we're going to take the second derivative, and well, that's also going to be equal to e to the x, right? E to the x has that special property where no matter how many times we take the derivative, it equals to itself, right? That's the special property of this. So if we go out to the nth derivative of this function is still going to be e to the x, right? No matter how many times I take a derivative, I'm just going to keep getting e to the x, e to the x, e to the x, right? All the way down to n and beyond that. Okay, so now for each one of these, I want to evaluate it at 0, right? Because it's the Maclaurin. So let x equal to 0. And figure out each one of these values. So then f of 0 is going to be e to the 0, which equals to 1. And this one, f, the first derivative, evaluated at 0, is e to the 0 as well. That's just equal to 1. And then f of 2, the second derivative, evaluated at 0, well, that's just e to the 0. That also equals to 1. And then the next derivative, the third derivative, evaluated at 0, well, that's also e to the 0. That's also equal to 1. And so on and so forth, and so on and so forth. And so the nth derivative of the function x, of the function evaluated at 0, is just going to be e to the 0, and that just equals to 1. Okay, so that means that this part here is just always going to be equal to 1. Good? Okay, so that means that so far we have that f of x is going to be equal to from 0 to infinity, and then all of the terms, okay, I'll write it out one more time. Valued at 0, all over n factorial, x to the n. So that means that if we write this out, we're going to end up with e to the 0, which is the original function. That's just going to be f of 0 times x to the 0 power, all over 0 factorial, plus, and then f1, the first derivative, evaluated at 0, divided by 1 factorial, x to the 1 power, plus f of the second derivative, evaluated at 0, over 2 factorial times x squared, plus f of the third derivative, evaluated at 0, over 3 factorial x to the third power, plus dot, 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 dot. Okay, and then we just saw that all of these terms become 1, 1, 1, 1, 1, or coming over here, this thing was just 1. So we can say that our function, f of x, is then simplified to be 0 to infinity of 1 over n factorial times x to the nth power. Good. Or combining it, we know that we were working with e to the x. So we're saying e to the x is equal to the sum as n goes from 0 to infinity of x to the n divided by n factorial. Good. Okay, what does this mean? This is the Taylor series expansion of e to the x, or the Maclaurin series since it's centered at 0. This is the Maclaurin series expansion of e to the x. And we can leave it like this, or we can simplify it a little bit and say that this is e to the x equals to, okay, if we have a 0, we end up with x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the second over 2 factorial plus x to the third over 3 factorial, and so on and so forth, so on and so forth. Or again, we can simplify that a little bit more and say that, well, this is just going to be a 1 plus, well, that's just going to be an x, plus, and then that's going to be x squared over 2 factorial, plus, that's going to be x cubed over 3 factorial, and then we can see the pattern after that. In fact, just to establish that pattern, I probably should have left this as x to the 1 over 1 factorial. Okay, so here it is. This is the Taylor series expansion of e to the x. And when is this going to be true? Well, it's going to be true as long as this converges. So we have to figure out, how does this converge? So to test for it, to see if it converges, why don't we check the ratio test? Right, so we're going to say, does this converge, or when does it converge? So then we're going to use the ratio test. Use the ratio test. And so if we use the ratio test, remember that we're going to test to see when is it true that the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, we want to show that that equals to some value L, and as long as that L is less than 1, it will converge. If that L is strictly greater than 1, then it diverges. And if that L equals exactly 1, then we're not sure. We're going to have to check it. It's inconclusive at that point. So what we want to do is this: figure out what values are needed, what values of x are needed in order for us to get a value that's less than 1. So we're going to do this. So let's use the limit as n goes to infinity of, and now I'm going to just copy this term down here. That'll be the a sub n term, x to the n divided by n factorial. That's the a sub n. And the a sub n plus 1 is going to be up here. This will be x to the n plus 1 divided by n plus 1. All of that inside the absolute values, right? So then this guy up here is my a sub n plus 1, and this guy down here is my a sub n. Okay, so let's simplify this a little bit. This means that the limit as n goes to infinity, it's going to be absolute value of, and I'm going to break this down a little bit. This will become x to the nth times x to the first power divided by n plus 1. Oh, sorry, n plus 1 factorial. Correction. So this is n plus 1 factorial, and this one was just n plus 1. Okay, so then I broke up this part here into these two. So now I'm going to separate this into n plus 1 times n factorial, and then that'll cancel out with that one. So then that's times the reciprocal of the numerator, so that'll be n factorial divided by x to the nth. I'm just flipping this guy upside down. All of that is still inside the absolute values. Okay, now, finally, some stuff will cancel. This will reduce with that, and this will reduce with that. And so the only thing that survives is the limit as n goes to infinity of the absolute value of x divided by n plus 1. Now, x is what we're looking for. What values make this converge? And so we don't know whether it's positive or negative, but n is positive numbers for sure. They're counting numbers, 1, 2, 3, 4, 5, right, out to infinity. So n plus 1 is never going to be negative, so we can get it out of the absolute values and separate it like this. This is the limit as n goes to infinity of, of 1 over n plus 1, right? And then that gets multiplied by the absolute value of x. And so as n goes to infinity, this gets infinitely large in the denominator. 1 over something that's growing out to infinity is going to grow towards 0. So that grows towards 0. And so it doesn't really matter what x is. No matter what x is, as long as it's some constant. It could be any constant. It could be a huge constant. 75 billion. Okay, 75 billion times 0, that's 0, right? So it just doesn't change. It's once you've chosen it, it could be anything, but once you've chosen it, it's a constant. A constant times 0 is 0. So that means that this is going to converge for all values of all values, right? X could be any value at all. So this is going to be equal to 0, which is definitely less than 1. That's all we really need to check for the ratio test. When is it less than 1? Well, it's always less than 1. So by the ratio test, the series we were working with, right, which we established was e to the x is this, converges for all real numbers, which means that the interval of convergence is going to be from negative infinity to positive infinity. Interval of convergence, which means that the radius of convergence is infinity, right? It's centered at 0, and its radius of convergence r equals infinity. Okay, so what does this really mean? What have we established? We established a different way of representing the function e to the x. That's what we've established. E to the x is a function, right? We can write it this way. F of x equals to e to the x power. This is a function. We can evaluate this. We can plug in values into here, plug them into there, we get a value. So for example, let's say equals let's say, for example, it equals 3. So what is f of 3? E to the 3. That's just 3 to the e to the power of 3. We can get a decimal representation using our calculator. So we can just take e to the power of 3, and we can get a pretty decent decimal, 20.085536. So there we go, approximately equal to that. Or we can go, wait a minute, okay, also e to the x is equal to this. So we can also say that e to the x, which was also equal to this infinite sum, as n goes from 0 to infinity, of x to the n over n factorial, is also going to be, it's going to result in us saying that e to the third power, it's also going to result in us saying that f of 3, which is equal to e to the third power, is also equal to the sum, as n goes from 0 to infinity, of 3 to the power of n divided by n factorial, right? So we can expand this out a little bit, just a few terms. And basically all we're doing is replacing the x with a 3. So when n is equal to 0, we get a 0. That's 3 to the 0 power is 1. And then 0 factorial is 1. So the first term is 1. Plus, the next term is going to be equal to 3 to the first power. 3 to the first power over 1 factorial. Plus, the next term is going to be equal to 3 to the second power over 2 factorial. The next term is going to be equal to 3 to the third power over 3 factorial. Plus, the next term is going to be 3 to the fourth power over 4 factorial, and so on and so forth, forever. So what we could do is just use our calculator to approximate this or do the first few terms and see that they begin to get close to that guy right there. So I'm going to just simplify this a little bit. This is 1 plus 3 over 1 plus 9 over 2. 2 factorial is 2. 3 squared is 9. Plus, this is going to be 27. 27 over 3 factorial is 3 times 2, which is 6. Plus, this is going to be 81. 3 to the 4th is 81. Divided by 4 factorial. 4 factorial is 24. Plus, dot, 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 dot. Okay, so let's use our calculator to show that this is starting to get close to that. It's approaching that. Okay, so the first term is just going to be 1. Plus, the next term is just going to be 3. Plus, the next term is going to be 9 divided by 2. So we get that. Plus, the next term is going to be 27 divided by 6. 27 divided by 6. Enter. So we get to 13. Plus, the next term is going to be 81 divided by 24. Enter. Okay, so I'm getting close, maybe a couple more terms. So let's go back here and expand this a little bit more so we get a little closer to the 20.08. Okay, so expanding this a few more terms. Okay, so we already had out to the fourth one, 3 to the 4th power. So we're just going to start adding some of these extra ones and see that we eventually get close to the value we wanted. So we're going to take the previous value and add to it 3 to the power of 5 divided by 5 factorial. And I get 18.4. And then the previous value, now we're going to do parentheses 3 to the power of 6 divided by 6 factorial. And we get 19.41. And the previous value plus, and now we're going to do 3 to the power of 7 which gives you that. Okay, so we started growing a lot in the first few terms, but now as I've been tacking on these extra terms, it hasn't been growing by that much. So it's like slowly creeping up closer and closer and closer to this 20. Let's do a couple more terms. So the previous value plus, and now I'm going to add the next term, that next term being this one. So that'll be 3 to the power of 8 divided by 8 math probability down factorial, close parentheses, enter. Okay, so now I'm getting really close. Add one more term, previous value, plus, and then the next term, which would be 3 to the power of 9 divided by 9 math factorial enter. Again, really close. And then the last one, previous number plus parentheses 3 to the power of 10 divided by 10 factorial. Enter. And you see we're getting closer and closer and closer to the exact value. Okay, so this is after going out to n equals to 10 terms, so there's 11 of them if we include the 0. So just including the first 11 terms, you see that I'm getting really, really, really close to the exact answer of e to the third power. So if I let this go out to infinity, eventually it'll be exactly the same answer as this one. Right? That's what we've accomplished. We got a Taylor series representation of e to the x, which means that we can evaluate e to the third power this way. E to the third power gives you this, or e to the third power, all we have to do is go into our Maclaurin series expansion and replace the x value with a 3, and you see that we get a pretty decent approximation. And this is, of course, valid for all real numbers, as we established with our ratio test. Okay, so since we established that e to the x can be expressed this way, this is a Maclaurin series expansion or Taylor series expansion, and we saw that in the case where x equals to 3, we were able to expand it like this. Well, then another really popular way to expand this is to let x equal to 1. So if we let e to the 1 power, well, e to the 1 power is just e, right? So e. And now we come in here and we replace the x with a 1. We'll end up with 1 to the power of n, which is always going to be equal to 1. And so that becomes the sum from 0 to infinity of 1 over n factorial. And so if we expand that out a little bit, we get that e equals to, when we put it in there as a 0, we get a 1 plus, and then when we get a 1, we get a 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, and so on and so forth, so on and so forth forever. So there's another fun way of expressing the value of e, right? And again, we can use our calculator and approximate this, and we know by other methods also an approximation of e, so we can match them. Okay, let's do another example. So find the Taylor expansion, or the Taylor representation. Find the Taylor series representation. Of the function f of x equal to ln of x at a equals to 1. Okay, so what does this mean? We're going to need to work on our expansion, right? If there's a Taylor series expansion for f of x, then we're going to say that ln of x is going to be equal to some infinite sum from 0 to infinity, and there's going to be derivatives, the nth derivative evaluated at a divided by n factorial times x minus a to the nth power, right? So here is what our Taylor series expansion is going to look like. So we need derivatives. So let's come back over here. F of x is equal to ln of x. The first derivative of x is equal to 1 over x. Okay, well, we can also rewrite this as x to the negative 1 power. All right, the second derivative of x is going to be equal to, let's bring down that negative 1 times x to the negative 2 power. Okay, and again, well, we could also rewrite this as negative 1 over x squared. And then the next derivative, f of 3 of x is equal to, we'll bring down that guy and becomes negative 1 times negative 2 x to the negative 3. And so now negative times negative becomes a positive. So this guy just becomes 2 times x to the power of 3 minus 3. or we can rewrite it as 2 over x to the cubed power. Let's keep going, a couple more, see if we see a pattern. And maybe for the sake of the pattern, I probably shouldn't have gotten rid of that 1. So that's really a negative times a negative becomes a positive, but I'm just going to leave the 1 there so that we can see a pattern. That's the third derivative. What about the fourth derivative? Fourth derivative of our function is going to be this guy. Okay, so now the pattern is going to be 1 times 2 times negative 3 x to the power of negative 4. And so this is going to stay negative now. And so if I wanted to simplify that, I would end up with 3 times 2 times 1 all over x to the power of 4. And there would be a negative here, right? So negative 1. All right, let's do a couple more, really establish this pattern. F of the fifth derivative of this function. Okay, so bringing that in front becomes 1 times 2 times negative 3 times negative 4 times x to the negative 5. Good, so now again, a negative times a negative, this is going to turn into a positive. And so we can simplify that a little bit by saying that this is 4 times 3 times 2 times 1 times x to the negative 5 power. Or we can rewrite it as 4 times 3 times 2 times 1 all over x to the positive 5 power in the denominator. So it becomes positive. Okay, so do we have a pattern here? What happens as we keep going, as we move on? So there's an alternating power thing, right? So when we had the second derivative, this thing turned out to be negative, right? Negative. And then the third derivative, it was positive. Negative times a negative is positive. The fourth derivative, we're back to this being a negative, right? There's a negative 1 component involved with that one. And then for the fifth one, we're back to this guy being positive. So it's going to alternate. So as I keep going down, and I want to find the pattern for the general one, dot, 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 what happens for the nth derivative of x? Well, there is a countdown thing that happens. I can see that part, 4, 3, 2, 1. And it looks like the countdown guy started at 1 less than the derivative, right? So the fourth derivative, the countdown started at 3. The third derivative, the countdown started at 2. The fifth derivative, countdown started at 4. Okay, so then this derivative, the countdown is going to start at n minus 1. So there will be an n minus 1 times an n minus 2 times an n minus 3, dot, 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 all the way down until we get to this 2 times 1, that kind of thing. Okay, so all of that can be just expressed as a n minus 1 factorial, right? So we can just eliminate all that and say, okay, a better way of expressing all that, more condensed way of expressing all that is to say that it's n minus 1 factorial. Okay, and then there's also this business of negative 1 to the power of something. So let's start by thinking, well, is it n? Okay, so would that match? If I left it like that, if I put a 5 here, then that would give me a negative 1. But the 5 should be positive, right? And then the 4 should be the negative. So I can either put a +1 or a -1 here to switch it off. And just so that it matches that, I'm going to make it a -1. Okay, so in other words, negative 1 to the power of n is always going to give me negative 1 if n is odd, and positive 1 if n is even. But in this scenario, I wanted the opposite. I wanted the odd ones to be the positive ones and the even ones to be the negative ones. So one way to tweak this is to switch it around and say add a 1 there. So now if n is an odd number like a 3, a 5, or a 7, it's going to turn it into an even, right? Plus 1. Any odd number, you add 1, you get to an even one. So in this scenario, then it'll flip it around. So the positive 1 will come if n is odd, and the negative 1 will come if n is even. And well, I could have added a 1, or I could have subtracted a 1. Same thing. If n is odd, if you take any odd number like a 3, a 5, 3, 5, 7, and we subtract 1, we'll get to an even one. Except for the case when n is 1, right? Because 1 minus 1 is 0, and that's neither even nor odd, so we just have to be careful about that. And so the reason why I chose that is just because it matches that one, right? And usually you'll get a nicer formula if you get some stuff to match, right? We like matchy-matchy. Okay, so next we have a power of x, x to the power of, and well, it looks like it matched every time. 4 there, 4 there, 3 there, 3 there. So it's going to be x to the power of negative n. Okay, so that's the equation. So again, we can also simplify this a little bit by saying that there's this negative 1 to the power of n minus 1 over there times n minus 1 factorial, and then the whole thing is all over x to the power of n. Okay, so now that we have all these derivatives and we have a nice little pattern for the nth derivative, we got to come back up here and figure out the value of the nth derivative at a. Right, so that's what we want to do at a equals to 1. So we got to find out all of these guys. So let me put lines here. Okay, so then we're always doing the case when x equals to a. So when x equals, so a for us equals to 1, and we want to find the nth derivatives evaluated at each one of these values. So we're going to get that for the first one, we're just going to get ln of 1, right? Replacing that value with a equals to 1, so x equals to 1. Okay, so for us, we have that x equals to a, which equals to 1 in this case. So we're going to have to evaluate f of a, which is equal to f of 1, which is going to be equal to ln of 1. So we're going to have f of x, which is really equal to f of a, which is really equal to f of 1, which is then equal to ln of 1, which is then equal to 0. So that first term is 0. Okay, then the first derivative evaluated at x, which is really the first derivative evaluated at a, which is really the first derivative evaluated at 1. So we end up with 1 over 1. 1 over 1, which equals to 1. Okay, I'm just going to skip some of that work there and say that the next one we care about is the second derivative evaluated at 1, which is going to be equal to negative 1 over 1 squared, which just equals to negative 1. Okay, the third derivative evaluated at 1, it's going to be this guy. That's just going to be equal to 2 divided by 1 to the power of 3, which is just going to be equal to 2. And then the fourth derivative evaluated at 1 is going to be equal to negative 1 times 3 times 2 divided by 1 to the fourth power, which really just equals to negative 6. Okay, so the fifth derivative evaluated at 1 is equal to 4 times 3 times 2 times 1 all over 1 to the 5th power, which equals to 4 times 3 times 2 times 1, which equals to 24. Okay, and so we have our pattern. So now then the nth derivative, evaluated at 1, is going to be this thing where we let this equal to 1. So it's just going to be negative 1 to the power of n minus 1, n minus 1 factorial, divided by, and then this 1 is the one that comes from here. This 1 is the one that goes here, because I'm replacing the x, to the power of n. Right, which we established, well, that's just equal to 1. So then that's just going to be this numerator. So it just simplifies to negative 1, the power of n minus 1, times n minus 1 factorial. Okay, so we figured out the nth derivative evaluated at 1 equals to this. So now we can come back up to our Taylor, right? So coming back to the original then, we have that ln of x is going to be equal to this, 0 of f of n evaluated at 1 over n factorial times x minus 1 to the power of n, right? And this is where a equals to 1. Okay, so now we have a formula for this guy. That's this. So we can say that that whole thing is then equal to the sum as n goes from 0 to infinity of negative 1 to the power of n minus 1 times n minus 1 factorial all over n factorial times x minus 1 to the power of n. Okay, so now we can simplify this a little bit, right? Because we know that if we start to expand this out, we'll end up with the following. We end up with n goes from 0 to infinity of, there's this negative 1 to the power of n minus 1, the alternating part. Let's leave this alone, factorial. And then in the denominator, we can expand that as n times n minus 1 factorial, and then x minus 1 to the power of n. So these guys cancel out, and we're left with just this. And so we have our equation for ln of x. So ln of x is really this as a Taylor series expansion. We're going to have this alternating. So we have negative 1, the power of n minus 1, divided by n, times x minus 1 to the power of n. Okay, so that looks pretty good. So now that we've plugged it all in, now we have to kind of pause and make sure that things make sense. Particularly, we have to be concerned with making sure that this pattern works starting at the beginning. We might have to tweak this a little bit. And so notice that if I let n equal to 0, we have a couple of issues. One, we would end up with negative 1 to the power of negative 1. Well, that's not really a huge problem. It's just that it doesn't really follow the pattern of raising it to an odd, even, odd, even, odd, even. Now it's raising it to a negative number, so that's unusual. But then the other real problem is that this is not n factorial anymore. We had taken the notation that n factorial, right, when we have n factorial, if we let n equal to 0, 0 factorial, we said, well, let's just let that equal to 1. Hole to go down, but 0 factorial is a 1. But this is not n factorial, this is just n. So if I let 0 go into there, we would be dividing by 0. So that's a problem. So if you notice, 1 is going to be okay. If we let n equal to 1, let's see what happens over here. if n equals to 1, it's just, 0 was kind of an issue, but okay, n equals to 1, we end up with a positive number. I'm sorry, we get a 0 here. Negative 1 to the 0 power is just going to be 1. So we end up with 1 over 1 times x minus 1 to the 1 power. When n equals to 2, we end up with a negative number, so negative 1 all over 2, and then x minus 1 squared. And then, okay, so things work out nicely. We don't have any other weird things happening beyond that. It was really just n equals to 0 that was an issue, right? Okay, and so if you notice, the very first one, n equals to 0, the first value to work with, if we come back up here, the patterns are not consistent. If you notice, we had alternatings, positive, negative, positive, negative, positive, right? But then the very first one was just 0. Is neither positive or negative, so it doesn't keep that consistency, right? It was really starting at this one, the first derivative at n equals to 1, that the pattern started to emerge. And the first value was just a 0. So for that reason, that motivates us to come back over here and say that this pattern is really just going to be started at n equals to 1. So we can come back over here and change this to starting at 1. Right? Starting at 1, we'll see that's the pattern that begins to work. Good? Because, why? Because the first time I did this, I got a 0. And then the pattern started to form. So I can just kind of say, well, let me just come up with a pattern for all of this. So that's why I have the sum starting at 1. And you're like, well, what about 0? N equals to 0. Well, that's okay. Luckily, it was a 0, so it doesn't really do anything. Good? Okay, so we're going to ignore that first one. Luckily, the result was 0 anyway. If it was some other constant, we can tweak it. But luckily for us, it was a 0. So I'm really only looking for a pattern for the rest of them starting at n equals to 1. And it's starting at n equals to 1, I get these patterns. 1, negative 1, 2. Okay. So the pattern will work from then on. And then next, we got to figure out, well, what is the radius of convergence for this guy? When is it going to work out? For what values of x is this going to be a valid representation of the Lx function? Lx equals to this, but for what values of x? Is it all real numbers? Is it always true? Or is there a domain that must be true? Okay, so to figure that out, we got to do our good old ratio test. Let's do our ratio test. So we're going to figure out the limit as n goes to infinity of the absolute value of, okay, so I'm going to copy that thing. That's going to be a little fraction down in here, and it's going to have a negative 1 to the power of n minus 1, and then there's an x minus 1, the power of n, and then all over n, and that's in the denominator. That's going to be my a sub n. And now in the numerator, we got to do the same thing, but the n plus 1. So then there's a little fraction up here. Its denominator is going to be n plus 1. And then this guy is raised to the negative 1 to the power of n minus 1 plus 1 just becomes n. Right? If I just raise this plus 1, I get to n. And then I get an x minus 1 to the power of n plus 1. All of that in absolute values. So we have a little fraction in the numerator. That's my a sub n plus 1. And then we have a little fraction in the denominator, which is this term here. This equals the limit as n goes to infinity of the absolute value of negative 1 to the power of n, x minus 1 to the power of n plus 1, all over n plus 1, times, and then we flip this guy around, we get n divided by negative 1 to the power of n minus 1, and then x minus 1 to the power of n. Good? Okay, so now we want to try and simplify this a little bit. Let's separate these guys. So this becomes the limit as n goes to infinity. Now, these n's do not cancel. Remember, they're not factorials. It's just n and n plus 1. So those guys do not cancel. But we do have a term of x minus 1 to the power of n plus 1, so we can separate that. It's negative 1 to the power of n, and then x minus 1 to the power of n times x minus 1 to the power of 1 all over n plus 1 times n all over negative 1 to the power of n minus 1. And then this becomes x minus 1 power of n in absolute values. Okay, so then this guy cancels with this one. This x minus 1 to the power of n, x minus 1 to the power of n. Those guys reduce. N and n plus 1 don't cancel, but I can pull them out of the absolute values because they're positive counting numbers, right? 1, 2, 3, 4, 5, out to infinity. So the absolute values don't affect them. And then here, minus 1 to the power of n, well, that's just going to alternate between positive and negative 1, positive and negative 1. This also alternates between positive 1, negative 1, positive 1, negative 1. So the division of the two is always going to be negative, right? Because when one is positive, the other one is negative. When one is net positive, the other one is negative. And that's always true for both of them, right? Because they're always off by one power. So there'll be a negative 1, but the absolute value gets rid of that. So we can pull that out of the absolute values and say that this is the limit as n goes to infinity of just the n over n plus 1 times, and then we'll have the absolute value of x minus 1. Good. So that guy survives. It stays inside the absolute values. This over this can come out of the absolute values, and then this guy and that guy are eliminated because there will be a negative 1. So absolute values gets rid of that. And so now the limit as n goes to infinity, okay, so then we do our usual little trick for this guy. Let's multiply by 1 over n over 1 over n. And then that'll give us the limit as n goes to infinity of 1 divided by 1 plus 1 over n times the absolute value of x minus 1. And so now the limit as n goes to infinity of this guy becomes 0, and so the whole thing becomes 1. So this whole thing just becomes 1 times this thing, x minus 1. And remember, the ratio test stated that as long as this is strictly less than 1, it will converge. And that's what we're looking for. So that's our result. We want x minus 1 to be within 1. That means that the radius of convergence is 1 equals to 1. And so it means that negative 1 must be less than x minus 1 less than positive 1. And so now if we add 1 to all three parts of the inequality, we get that 0 must be less than x must be less than 2. Okay, but now we got to check the endpoints, right? So we got to figure out what happens here. Check the endpoints. Right? Because what we have so far, just to kind of bring it together, we have so far is that f of x, which is equal to ln of x, can be expressed as this Taylor series expansion starting at 1 of negative 1 to the n minus 1 x minus 1 to the power of n all over n. Negative 1 to the n minus 1 x minus 1. Okay, so we have this, and it's good on this interval. We just have to check the endpoints, right? So let's check when x equals to 0, check. When x equals 0, okay, what happens there? When x equals to 0, that means we'll replace this value with a 0. So let's see. This will be 1 to infinity of negative 1 to the n minus 1 blank minus 1 to the n power all over n. And so replacing that 0 right there with a 1. And we're going to check, does this converge? Does it not converge? Does it diverge? Okay, so 0 minus 1, that's just going to be negative 1 to the power of n. So that'll be equal to this, negative 1 to the power of n minus 1, and then we'll have another minus 1 to the power of n. Forgot my, and then all over n. Good. Okay, so now we can combine these guys. So this equals that, and then let's move it over here. So now this is going to be the sum as n goes from 1 to infinity. And if we bring them together, they have the same base. That means we add the exponents. We'll have negative 1 to the power of 2n minus 1. All of that all over n. Good. And now let's explore what this looks like. Initially, I think we would all think, oh, this is just the alternating. It goes negative 1, positive 1, negative 1, positive 1. But if we pay attention to the exponent, n equals to 1 times 2, not times, correction. N equals to either a 1 or a 2 or a 3 or a 4, right? Dot, 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 dot. So that when we have negative 1 to the power of n, it's the exponent is alternating between odd, even, odd, even, odd, even, right? So that's really the point, that as n changes through its various natural counting numbers, then we end up getting negative 1 to an even power. We get negative 1 to an odd power, right? Well, the other way around. Negative 1 to an odd, right? When n equals to 1, n equals to 1, well, that's odd. We'll get a negative 1. When n equals to 2, we'll get an even, which means that this is going to be a positive, and so on and so forth. And that's what generates the alternating between positive and negative and positive and negative. Okay, so what does 2 to the n represent? 2 times n. 2 times n is a multiple of 2, right? 2n when n is 1, 2, 3, 4, 5. When n is 1, that'll be a 2. When n is 2, that's a 4. When n is 3, that's a 6. So this is always a multiple of 2. Multiple of 2, aka this is always even. 2n is always an even number. And so if 2n is always an even number, then that must mean that 2n minus 1, we take it something that's always even, and we subtract 1, well, this is always going to be odd. So even though it kind of looks like it's alternating, that it's going to cause it to go negative 1, positive 1, negative 1, positive 1, really what we have here is something that's always odd. And what happens when we take negative 1 to something that's always going to be odd? Well, it's always going to be negative 1. So this sequence then, this series then can simplify to negative 1 to infinity of just 1 over n, negative 1 over n. Good. So this is just always negative. And negative 1 to the power of an odd is always negative 1. So we just have negative 1. Now again, this is not alternating. This is just negative 1. So we can easily pull that out, right? It doesn't have anything to do with n. So we can pull it out as a constant and say that this is negative 1 times the sum as n goes from 1 to infinity of 1 over n. Does that converge? Well, hopefully we remember that this is one of our very famous series. This is the harmonic. Pops up all the time, harmonic series. And we know the harmonic series diverges. Right, so we've established that when x equals to 0, this whole series is going to diverge, so it's not part of its domain. Right? So if we come back up here, we checked this one, and note, this is not going to work when x equals to 0. What about when x equals to 2? Let's check that one. So now we want to check x equals to 2. And so again, we have that ln of x is equal to the sum as n goes from 1 to infinity of -1 to the n minus 1, x minus 1 to the power of n, all over n. And so we're going to replace x right here with a 2. And so we'll end up with the sum as n 2 minus 1, we replace the x with a 2, we just get a positive 1. 1 to the power of n all over n. And 1 to the power of n is just going to be 1. So that term, that part of it just kind of disappears and becomes the sum as 1 to infinity of -1 to the power of n minus 1 all over n. And now this guy, well, now this will be something that alternates between positive, negative, positive, negative, positive, negative, where the first one, right, when n equals to 1 becomes positive 1. And then when n equals to 2, we get a negative 1, and so on and so forth. So this is our classic alternating series, a series that we can see converges by the alternating series test, right? Alternating series test. We have a component that's alternating between positive, negative, positive. We have that part. And then the other part is 1 over n. And there were two things to consider. One was to make sure that they were converging to 0. Okay, so 1 over n, the limit as n goes to infinity of 1 over n is definitely going to go to 0. That was one of the conditions. And the other conditions was to show that it's decreasing. And yes, 1 over n is decreasing. We could do some work there to show the derivative, and the derivative is negative, so it's going to be decreasing on the interval on x being greater than or equal to 1, for sure. Okay, so by the alternating series test, this converges. So converges by the alternating series test. Converges by AST, alternating series test. Okay, so that means that x equals to 2 is going to be part of the domain. So let's bring it all together. We have that ln of x can be represented as a Taylor polynomial, a Taylor series by this one, from n goes from 1 to infinity of -1 to the power of n minus 1, x minus 1 to the power of n all over n. And this is valid. This will work out as long as x is a member of the interval 0 to 2, where we do not include the 0, but we do include the 2. From 0 to 2, inclusive of the 2, this is going to work out, or any value there. For any value outside of that, then we cannot say that this Taylor series will be equal to that function, right? So this Taylor series representation of that function is only valid on this domain. All right, let's look at your homework. Start picking away at some of these. This is the homework exercises for Chapter 11, Section 10. Use the definition of the Taylor series to find the first 4 non-zero terms of the series. Okay, hopefully that one's not too bad. You just have to find the first 4 terms. Okay, let's start with these guys. Let's do number 13. That's a classic one. Find the Taylor series for f of x using the definition of the Maclaurin series. And also find the associated radius of convergence. So let's do f of x equals to cosine of x. Okay, so find the Maclaurin series for cosine equals for f of x equals to cosine of x. So the first thing I would recommend is, jump over and look at your formula, right? If there is Maclaurin series, it's got to look like this. N goes from 0 to infinity of f of n of 0 divided by n factorial x to the nth power. Right? That's what it looks like. Okay, so we need derivatives. 1 derivative, 2 derivatives, 3 derivatives, all the way out to the nth derivative. And then we're going to evaluate each one of them at 0 and hopefully find a pattern that we can use so we can express the whole thing with that pattern. And then put it back in here so we can figure out what this is, and then we're going to determine whether it converges, diverges, and what the interval of convergence is. Sounds easy, right? Okay, so let's get started. So first of all, step 1, you're going to need lots of derivatives, right? Step 1, derivatives. Okay, so the first function is cosine x. The first derivative of this function is going to be f1 of x. Well, the first derivative of cosine is negative sine x. Then we got to go to the next derivative. The second derivative of our function is going to be the derivative of this one, which is going to be equal to negative cosine of x. And then we're going to need the third derivative. The third derivative with respect to x is going to be equal to, again, we need the derivative of cosine is going to be negative sine, so we're going to get a positive sine x. And then the fourth derivative with respect to x is going to be equal to cosine x. And then the fifth derivative with respect to x is going to be equal to negative sine x. Okay, so now we need to evaluate each one of these at 0. So f of 0, right, that's when x equals to 0. That's just going to be with the cosine of 0, which means it's a 1. And then for the first derivative, f of 1, evaluated at 0, that's going to be negative sine of 0. Sine of 0 is 0, so this is just going to be equal to 0. Good. Then we need the next one. The second derivative evaluated at 0 is going to be negative 1 cosine of, so this will be a 0. Second derivative evaluated at 0 gets you negative cosine of 0. Cosine of 0 is 1, so this is going to give us that negative 1. Good. Okay, the third derivative, that's going to be f of 3 evaluated at 0. That's going to be equal to sine of, and then this is evaluated at 0. So that's just going to give us a 0. The fourth derivative, evaluated at 0, is going to be cosine of 0. Which gives us a 0 there and a 0 there, which means this is positive 1. And then the last one I have on here, f, the fifth derivative, evaluated at 0, it's going to be negative sine of 0. So we get a 0 there and a 0 there. So sine of 0 is 0 times negative 1 is still going to give me a 0. Okay, this is going to be a pretty tricky pattern. So you know what? I want to go one more just to really kind of see what's going on with this pattern, because it's really kind of baffling me a little bit, right? Okay, so let's see. Let's go out one more term. So f of 6, sixth derivative. Well, we're still going to keep this minus. That's going to become minus cosine of x. And so the sixth one is going to be f of 6 evaluated at 0 is going to be equal to negative cosine of something. And evaluated at 0, cosine of 0 is 1, so we'll go back to negative 1. Okay, so let's see the pattern. The pattern starts off at 1. Right, so here's our pattern. It's 1, then 0, then negative 1, then 0, then 1, then 0, then negative 1. Okay, and then these are all the terms that go in our Maclaurin series right in here. Okay, so if I expand this guy out, if I expand this, I end up with the first one. Okay, that's just going to be f of 0 all over 0 factorial. We've established that that means it's a 1. And then x to the nth power. So x to the 0 power. Okay, so that's just replacing 0 there, 0 there, 0 there. Okay, plus when n equals to 1, we have the first derivative of our function evaluated at 0 divided by 1, and then we have x to the, or 1 factorial, x to the 1 power, plus f evaluated at the second derivative, evaluated at 0, all over 2 factorial, x to the second power, plus, okay, seeing the pattern here, to the third derivative, 3 factorial, x to the third, good, and so on and so forth. Okay, but now f of 0 was a 1, so we're going to come in here and we're going to change each one of these. So let me separate this here. Okay, so now this is going to be equal to, okay, f of 0 was just a 1, and 0 factorial, that's just going to be 1. So this is also just 1, so it just starts off with 1. Okay. The next one is the real interesting one. The next one is going to have a 0 for this part. So it's going to be 0 over 1 factorial times x to the 1 power plus, and now the next one is this one. This one's going to be negative 1. So negative 1 over 2 factorial x to the second power plus, now the third one has a 0 again. 0 over 3 factorial x to the third power, and let's keep going with this pattern. The next one is going to be a 1, right? If this has a 4 here, let's erase that and expand this just a little bit more. The next one is going to be f of 4 evaluated at 0 divided by 4 factorial to the 4th power, right? That's the next one. The fourth derivative evaluated at 0 is going to be a 1. So that's just going to be 1 over 4 factorial x to the 4th. Okay, so the powers are easy enough. Power of 1, power of 2, power of 3, power of 4. I think we feel pretty comfortable saying the next one in the pattern is going to be x to the 5th power. Good. And then the factorials also 1, 2, 3, 4. Pretty comfortable noting that the next one is going to have a 5 factorial here. So that part's pretty easy. But then if we come back over here, we see that this one is going to be 0. Well, anytime we have a 0, it's going to disappear, right? So when all the powers are odd, let's pay attention to this pattern, right? Patterns, this is all about patterns. Whenever we have these odd exponents, whenever we have the odd exponents, there's a factor of 0. So they disappear, is the point. So let's just simplify that and say it's 1 plus 0, plus this thing. Okay, so that's going to be negative 1. Okay, that's just a minus. So let's have this thing that changes. We have a minus, so minus that guy. And then it's x squared over 2 factorial plus 0, right? The odd one disappears again. And then we have a positive, so plus x to the 4th over 4 factorial plus, and then the next one is 0. It's going to disappear. All the odd ones disappear. And then we see that the next one is going to be 6. 6 gives me back to a negative 1. So I know that the next one is going to be minus, and it's going to be x to the 6th power over 6 factorial. Good. So all the odd ones disappear. I can just get rid of them and say it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so forth. Okay, so I see that I'm only keeping all the even powers, and the pattern, I guess, could be continued here if we had an x to the 0, 0, 2, 4, 6, and to the 0 power, x to the 0 power would still give me a 1. So just to kind of establish that pattern, to keep going, I could say that this is x to the 0 over 1 factorial, and then we'd end up with the same pattern. It's x to the 6th over 6 factorial plus dot, 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 dot. Okay, so now if we can find a way to express all of this using a Riemann sum, there is some component that's alternating between positives and negatives, and so, I mean, this could be an n, or it could be an n plus 1, depending on how we want it to go. It depends on whether we want to start with a positive or a negative, right? So that part of it will help us figure this out. But it'll also depend on whether I want to start with a 0 here, or maybe I want to start with a 1. Right, so we just kind of play and check with this a little bit, guess and check for a little bit, and figure out what we need. So let's say I started off with a 0. If I start off with a 0, it seems to be fitting this pattern so far. And then there seems to be something to do with all the even ones, right? So I don't want to be counting by ones. I want to be doubling everything. So it looks like maybe 2n factorial would work out. When n is 0, I get that first one. I get 0 factorial, which is equal to the same thing as this. So let's change this to be 0 factorial. Either way, this equals 1. Right? X to the 0 divided by 0 factorial is still equal to 1. So that saves our pattern. And the only reason I did that is because now this works. 0 gives me 0 in the denominator. 1 gives me 2. 2 gives me 4. 3 gives me 6. And now this is the same as the exponent, so this has to go to the power of 2 to the n. Right? And this goes from 0 to infinity. Okay, so it's a bit of a guessing and checking. So I kind of guessed what the pattern is. Practice helps. And then we're just going to guess and check it. So now that we kind of guessed what it is, we can just kind of expand it out a little bit and and make sure that in fact we're getting this pattern out of this, right? So try a few of these guys. Okay, so what did we get? We got that. All of this tells us that f of x, which is equal to cosine of x, has a Taylor series representation given by this. And if we wanted to expand this out a little bit, when n is 0, that's all going to turn into a giant 1. When n is 1, we'll end up with a minus. And then n is 1, we'll end up with an x squared over 2 factorial. When n is 3, I'm sorry, when n is 2, we'll end up with a positive, and then we'll get a 4 x to the 4th all over 4 factorial. Right, so I'm just guessing and checking, so now I'm confirming that in fact when n is 0, we get that one. When n is 1, we get that one. When n is 2, we get that one. And that matches with these guys. So we did a good job of figuring out the pattern that will give us that. And of course, this goes on forever. The next one's minus x to the 6th over 6 factorial plus dot, 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 forever. So we have ourselves a Taylor series representation of cosine. And of course, because it's centered at 0, then it's also, in fact, a Maclaurin series. Okay, so now we have to figure out the interval of convergence. To do that, we have to do our good old-fashioned ratio test on this one, right? When does this converge? So to figure that out, let's do the ratio test. Ratio test. And so the ratio test will be the limit as n goes to infinity of a giant absolute value. And then in the denominator, we're going to copy this. Negative 1 to the nth power x to the 2n divided by 2n factorial. So that's our denominator. That's our a sub n. And now in the numerator, we're going to have another giant fraction. We're going to have every n is replaced by an n plus 1. So this would be negative 1 to the n plus 1. X to the 2 times n plus 1. Be careful that the 2 multiplies by n, so 2 must multiply by n plus 1. Okay. And then in the denominator, we'll end up with 2 times n plus 1 in parentheses factorial. Right? So in other words, the 2 multiplies by whatever the input is, and the input is n plus 1, so all of it needs to multiply, meaning that I'm going to have to distribute this little 2 into there and into there before we take the factorial. Right? And then up here, we distribute that little 2 into there and that little 2 into there. Okay, so now we can simplify this. This will become the limit as n goes to infinity of, and we still have this giant absolute value. We're going to have to distribute that guy, so we'll end up with negative 1 to the power of n plus 1, x to the power of 2n plus 2, when we distribute that little 2, and then divided by, and then down here we'll end up with 2n plus 2 factorial times the reciprocal of the denominator. We'll end up with 2n in parentheses factorial divided by negative 1 to the power of n and then x to the power of 2n in absolute values. Okay, all right, so now we got to further continue the process of simplifying this a little bit. Easy pickings is to separate this, right? We know that if we're adding the exponents, that means that we can separate them into the product of two factors. So this will be the limit as n goes to infinity of the absolute value of negative 1 to the power of n plus 1. We'll leave that alone. And then this becomes x to the power of 2n times x to the power of 2. That's how we separate this term. And then this one's a little tricky, so let me refresh your memory on what this means. When we have n factorial, it means n times n minus 1 times n minus 2, right? It's a countdown starting at n, dot, 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 dot. And that countdown doesn't stop until we have 3, 2, 1, we end, right? So it's a multiplication of all of those terms, all those factors. Okay, so if we had 2n plus 2 in parentheses factorial, that means that that first term is 2n plus 2. And if we start the countdown, then we'd subtract 1. So the one right below this one is going to be 2n plus 1. And the one right below that is just going to be 2n. And the one right below that would be 2n minus 1. And the one right below that would be equal to 2n minus 2, dot, 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 dot. Eventually, you're going to run into n, and then n minus 1, and then n minus 2, dot, 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 dot. Eventually, you'll get down to 3, 2, 1, right? Depending, of course, on the value of n. Okay, so that's how we can express this guy. But of course, if we instead just express the first couple of terms, 2n plus 1, and then we can say that the rest of this, all of that, is really just 2n factorial. So the product of these three things, this times this times this, equals this one. And that's what we're going to do right here. I'm going to replace this with that. It's going to be equal to 2n plus 2 times 2n plus 1 times 2n factorial. Right? And that's this guy. And then we want to continue to simplify. Okay, so let me erase this. Hopefully that made sense. Okay, so now we're just going to copy this part over here. We end up with 2n factorial divided by negative 1 to the power of n, x to the 2n power in absolute values. Okay, and so now finally we get to cancel some stuff. This will reduce with that, and this cancels with that. And so the only things that survive the cancellation are this term, this one, and that one. Now these two, this one and this one, okay, those are things that alternate, right? Depending on whether the exponent is even or odd. It might be negative 1, positive 1, negative 1, positive 1. Same thing over here, depending on whether n is even or odd. This whole term will be negative 1, positive 1, negative 1, positive 1. But notice that the exponents are off by exactly one value. So whenever n is even, so if n is even, that means this one's going to be odd. And when n is odd, that means this one's going to be even. They're always off, which means that the division of this divided by this is always equal to negative 1. Always equal to negative 1. And it's inside the absolute values, so then that just simplifies to positive 1. Okay, so we're just going to ignore those moving forward once I pull it out of the absolute value. Now also, n is counting numbers starting at 1, 1, 2, 3, 4, 5, all the way out to infinity. That means that this part is positive always. This part's always positive as well. And when we multiply them, we're going to get another positive value. So the absolute values do not impact this one. Okay, so we can simplify that and say that this is equal to the limit as n goes to infinity of, let's pull out these guys. That'll be just 1 over 2n plus 2 times 2n plus 1 times, and then we have this like that. Okay, well, so this and this I got rid of easily since they're just negative 1, so the absolute value will make them positive 1. And then for any value of x, when I square it, I get exactly a positive number. So the absolute, right? We don't need to write that. So I can just say that this is equal to the limit as n goes to infinity of, and then I can just write it this way, x squared all over 2n plus 2 all over 2n plus 1. Okay, and so what's happening as n goes to infinity? The numerator stays the same, right? Once a value of x has been chosen, right? X can be any number at all, but once a value has been chosen, then the numerator is a constant. Like let's say x is 7 or x is 45 trillion. It doesn't matter how big or how small. X could be negative, it could be positive, it could be a decimal. But once something is chosen and placed in there, it becomes a constant. So the numerator is a constant. The denominator, on the other hand, is growing. 2n plus 2 is growing. It's getting bigger and bigger and bigger. And then we multiply that times 2n plus 1. That's going to be even bigger. So clearly the denominator is growing toward infinity. It's getting infinitely large. So a constant divided by something that's growing infinitely large, this whole thing is going to be equal to 0. Right? The limit of this whole thing is always equal to 0. And okay, don't forget that the whole point of this is that we were doing the ratio test. And so by the ratio test, we know that whenever we get a value that is less than 1, then we know that by the ratio test that it's going to converge, right? So that means that, so what we can conclude is that by the ratio test, we've concluded that the sum as n goes from 0 to infinity of -1 to the power of n plus, n minus n, to the power of n, x to the 2n, all over 2n factorial will converge for all real numbers. Right? In other words, the value r, the radius of convergence. And so we established that cosine of x is equal to sum from 0 to infinity of -1 to the power of n, x to the power of 2n, 2n all over 2n factorial. And this is valid, this is true for all real numbers. For x being any number, for x being any number from -infinity to +infinity, right? The radius of convergence infinities, or the radius of convergence r equal to infinity. Okay, so we found the Maclaurin series representation of the cosine function, obviously centered at 0 since it's the Maclaurin series. Okay, so we answered our question from number 13, but we can add one more thing now, a bonus. It wasn't part of the question, but now that we have cosine this way, we can also think about what sine is then. So what is sine now? F of x, let's put note the bonus, that if we had the function g of x equals to sine of x, sine of x is related to cosine of x in that, similar, it's close to the derivative of cosine of x, except this is going to give us an extra -1, so we got to toss in that -1 times the derivative of cosine of x. But we just established that cosine of x is equal to this as its Maclaurin series representation. So we'll have -1 times the derivative with respect to x of this thing. So that would be n goes from 0 to infinity of -1 to the power of n, x to the power of 2n all over 2n factorial. Okay, so now remember, we're able to take the derivatives term by term. So if this confuses you, then we could expand it out and say, well, it's the derivative of, and we already had this expansion. It was equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, 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 right? That was this expansion. Okay, so now we can take derivatives one term at a time. This is -1 times. Okay, the first one is going to be 0. So we'll end up with a 0. And now the derivative of the first one, remember, it's just with respect to x. And so with respect to x, this is some constant. This is some number. So don't worry about the derivative of 2 factorial. That looks messy. But that has nothing to do with the x. So it'll end up being minus 2 times x to the first power all over 2 factorial. Yeah, we can reduce, but let's leave it alone so we can see the pattern. Plus, and then we bring that out in front, and then we'll get a 4 x to the third power divided by 4 factorial minus 6x to the fifth power all over 6 factorial plus dot, 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 dot. Okay? So now notice that the 2 and this 2 can reduce to give you 1 factorial. This 4 and this 4 factorial can reduce to give me a 3 factorial and then a 5 factorial. And so the pattern is getting a little bit easier to see. It would be 0 minus x to the first power over 1 factorial plus x to the third power over 3 factorial minus x to the fifth power over 5 factorial plus dot, 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 dot. Okay, and then we can distribute this minus across. It's going to change all those signs. Of course, that's just a 0, so let's get rid of it. Well, it doesn't matter. So that's going to be 0, and then the first one after that is going to be positive x to the first power over 1 factorial plus, and then the next one is going, oops, and then the next one is going to be minus x to the third over 3 factorial, and then plus x to the fifth power over 5 factorial, and then minus, and then plus, and then minus, and then plus. Okay, so the pattern looks pretty good. Okay, so now what we want to do is find a way to represent this all as a Riemann sum. And there's a bit of a guessing and checking. Try different things and see, make sure, confirm that you're getting what you want. Okay, so we have some sort of Riemann sum. And things will vary a little bit depending on whether you want to start off with 0 or if you want to start off with 1. Maybe you want to start off with 2. It depends. It will vary. But 0 or 1 are the most popular ones. This will go out to infinity, of course. And then let's look at each part here. How do we guarantee that all the terms give us odd ones? One nice thing to do, sort of a shortcut, is to just say n equals odd here, and then people will know, okay, only let the counter here go 1, 3, 5, right? But we want to avoid that. There are some areas of math when they do things like that, but then that's just not something we want to get into right now. So we want to continue to let n equal all the counting numbers, not just the odd ones, starting somewhere. So if we start with 1, then we want to go 1, 2, 3, 4, 5, 6, 7. If we start with 0, 0, 1, 2, 3, 4, 5. Okay, so how do we do that? Well, we want to note this. As we said earlier, 2n is always going to be all the even numbers, right? As n goes from 1 and 2 and 3 and 4, 2n is then going to be equal to, when n is equal to 1, that's going to be a 2. When n is equal to 2, that's going to be a 4, then a 6, then a 8, then a 9, and so on and so forth. When n is equal to 0, we can start off at 0, n equals to 0. Okay, and so if this is how we describe all the even numbers, then the way to describe all the odd numbers is to do 2n plus 1, right? So when n is equal to 0, then we end up with, when n equals to 0, we end up with just the 1. When n equals to 1, then we get 2 plus 1, that gives us 3. When n equals to to 2, we get 4 plus 1 is 5, and so on and so forth. So that's how we guarantee that we hit all the odd ones. Okay, so if we start off at 0, and then we let this go out to 2n plus 1, then 0 there gives me the 1, then 1 gives me the 3, then 2 gives me the 5, and so on and so forth. Okay, the denominator is going to have the exact same value factorial. So just looking at patterns, I'm going to guess that it's this one, 2n plus 1 factorial. Good. And the alternating part of it, I want to start off with a positive, so I have a negative 1 to the power of something, and that power could be a 0. That works. If I let it be 0, then it starts off with positive, so let's let that equal to that. Okay, so here it is. This is the Taylor series representation of our sine function, which we got by knowing our cosine one. So kind of zoom out a little bit. Maybe that's a little too much. So we had our cosine, right? Our cosine function representation, a Taylor series representation of our cosine function. Here it is. And then we knew that there was this relationship between sine and cosine, that the derivative of cosine is going to be really close to the sine, except off by a -1, so we can just kind of adjust it a little bit. And then because we knew the Taylor series representation of cosine, then we can just manipulate that a little bit. So we didn't have to go through the process of doing derivatives and evaluating things. We can just derive this one based on that one. Right, so we start to see some of the magical powers of Taylor series. Okay, so we tweaked it, moved it around, pushed it around, and eventually came out with this. So we're saying that this is the Taylor series representation of sine. And because we got this one based off of the cosine, it turns out that they have the exact same radius of convergence. I don't have to go through the process of finding or using the ratio test on this anymore because I got it through this process. So they will have the exact same radius of convergence. So we're saying that sine of x, the sine of x function, is equal to this. This is its Taylor series representation. And this is good for x being a member of -infinity to +infinity. So this Taylor series representation is going to work for any value of x. And so it's going to have a radius of convergence of infinity. Right? So this is two important classic Taylor series representations.